Okay, let's unpack this. For decades, the relentless progress in our electronics felt almost like magic, didn't it?
Oh, absolutely.
Smaller, faster, cheaper chips, year after year. But what if I told you that the very fundamental way we construct computer chips, the silicon bedrock of our digital world, is currently undergoing a profound transformation?
A tectonic shift, really.
Yeah, we're talking about a re-architecture as significant as it gets in semiconductors.
That's a crucial observation. Today, we're diving into the fascinating world of chiplets and heterogeneous integration.
Oh,
Our mission is to demystify why this modular approach isn't just a trend, but a necessity, replacing the traditional monolithic chip and becoming absolutely essential for continued innovation. In everything from your smartphone to the colossal AI data centers driving our future.
right. We've sifted through a stack of cutting-edge research and industry insights, and we're going to distill it down to the most important nuggets, give you that shortcut to being truly well-informed on a topic that's quietly reshaping our tech landscape.
Sounds good.
So for generations, Moore's Law was the semiconductor industry's North Star, right? More transistors, more power, roughly every 2 years. It was an incredible run.
It really was. Defined an era.
But our sources reveal that this monolithic era, where everything, all those billions of transistors, was crammed onto a single piece of silicon, has finally hit some unavoidable and intractable challenges. It simply couldn't continue in the old way, not without significant trade-offs.
Indeed, there were two primary walls the traditional monolithic approach slammed into. First, the escalating costs and sheer complexity.
Just mind-boggling costs, I imagine.
Absolutely. Consider manufacturing features as tiny as single-digit nanometers.
Yeah.
The fabrication facilities, the lithography systems, those are essentially high-tech printers etching these microscopic patterns onto silicon wafers.
Right.
And the entire design process have become astronomically expensive. And when you're dealing with a single chip that might contain well over 100 billion transistors, you face what's called the yield problem.
Ah, yes, the yield.
A single microscopic defect on that massive, intricate piece of silicon renders the entire device unusable.
The whole thing. Just gone.
The whole thing. That leads to immense costs and waste, making the traditional single-die approach financially unsustainable at the bleeding edge.
Wow.
The second major hurdle is purely physical: power dissipation and thermal management.
The heat problem.
Exactly. Pack more and more transistors onto a single die, and the power density skyrockets. This leads to a phenomenon known as dark silicon.
Our silicon. Okay.
It means a significant portion of a chip's cores and logic must be throttled or deactivated entirely just to prevent the device from overheating.
So you have the power, but you can't actually use it all at once.
Precisely. So while a chip might contain hundreds of processing units, it can't operate all of them at full performance simultaneously. Its theoretical potential often far outstrips its usable capacity.
So the very success of making chips denser and more powerful paradoxically led us to a dead end. The quest for more power and smaller features made them too expensive to reliably manufacture and too hot to run efficiently. It's almost ironic, isn't it?
Absolutely. Physics has a way of reminding us who's in charge, but that pressure also sparks the most ingenious solutions.
Okay, here's where it gets really interesting. If the old approach hit a dead end, what was the breakthrough insight that led the industry towards a new modular approach? What's the fundamental shift in thinking?
That fundamental shift led to modular design. This new paradigm introduces chiplets.
Chiplet, like little chips.
Exactly. Imagine a chiplet as a small, specialized building block, optimized to perform a specific function, maybe a set of CPU cores or memory, or a networking interface.
Okay.
Instead of attempting to put all these diverse functions onto one gargantuan monolithic chip, you distribute them across multiple discrete chiplets, all working together within a single package. And this modular vision is realized through heterogeneous integration. This is far more advanced than just stacking chips.
Right, it's more complex.
It's about assembling diverse electronic and even non-electronic components into a single compact device. The crucial part is that these chiplets are tightly coupled on a common substrate,
Tightly coupled.
meaning their electrical connections are much closer and more efficient than in a traditional circuit board design. This allows engineers to combine components built on different process nodes, essentially, different generations of manufacturing tech.
Different generations on one package.
Yes. Using different process types like analog and digital, or even sourcing them from different foundries, all into one powerful system.
So it's like breaking down a giant, incredibly complicated puzzle into smaller, more manageable pieces. The sources highlight powerful advantages this modular approach brings, directly addressing those problems we just discussed with monolithic chips. Why should our listeners care about this beyond the technical details?
Well, you should care because this approach tackles those core problems head-on. One of the biggest drivers is dramatically improved manufacturing yield and cost efficiency.
Ah, back to the yield.
Exactly. By breaking a large, complex die into smaller chiplets, if one chiplet has a defect, you only lose that small, inexpensive piece, not the entire costly device.
That makes so much sense.
This significantly boosts manufacturing yield. Plus, you can optimize costs. You can put less critical components like I/O controllers on cheaper, more mature process nodes,
Okay.
while the most advanced, high-performance CPU cores can go on the bleeding edge, costly nodes. This strategic separation optimizes the overall system cost without sacrificing critical performance where it matters most.
Smart. Very smart.
Beyond the economics, there's design reusability and faster innovation. Chiplets essentially become pre-verified building blocks. Think of them as high-tech Legos
Legos, I like that analogy.
that can be reused across a wide range of products. This enables parallel, independent development of individual components, which slashes R&D costs and accelerates time to market. It's a game changer for bringing cutting-edge technology to consumers faster.
Faster innovation, lower cost. What else?
And finally, scalability and flexibility. Chiplets give designers the ultimate freedom to mix and match components, creating application-specific architectures.
Tailor-made chips.
Pretty much. Perfectly tailored for everything from high-performance computing and AI to specialized edge devices. No more one-size-fits-all compromises. Now, there are some complexities, sure, like managing interconnect performance and thermal challenges between dies.
Right, it's not magic.
No, but the overall benefits overwhelmingly compel the industry in this direction.
Okay, so we got these incredible Lego blocks, these specialized chiplets, but how do you actually snap them together to make a super powerful system that performs like a single seamless unit? That's where advanced packaging and sophisticated communication standards come in, right?
Exactly. Advanced packaging is no longer just the final step in manufacturing. It actively enables a system's performance.
It's part of the design itself.
Precisely. One key technology is 2.5D integration. That's where multiple chiplets are placed side by side on a passive silicon interposer or a small embedded silicon bridge.
An interposer, like a little connecting layer.
Yep. This interposer acts as a high-density wiring layer, providing a communication pathway between chiplets that's far more performant than a traditional circuit board. Intel's Embedded Multi-Die Interconnect Bridge, or EML,
EMIB, okay.
is a great example of this. It shortens signal paths dramatically to connect, say, an FPGA die to I/O and memory chiplets. Then there's 3D stacking.
Stacking them up.
Stacking dies vertically using through silicon vias, or TSVs. That offers the highest density and shortest paths, but also introduces the most complex power and thermal challenges due to the vertical heat concentration.
Makes sense. Heat rises, right?
Sort of, yeah, it concentrates heat.
Okay, so the physical connections are one thing, but then they need to talk to each other. Yeah. What language do these chiplets use? Is it a universal language, or do we have a digital Tower of Babel situation on our hands?
Good question. Initially, it was a bit of a Tower of Babel. The first chiplet products relied on vendor-specific proprietary interfaces.
Like everyone speaking their own dialect.
Pretty much. For example, Intel developed its Advanced Interface Bus, or AIB. That's a short-reach, parallel die-to-die interface known for high bandwidth, power efficiency, and remarkably low latency.
Low latency is key.
Very key. Significantly shorter latency than typical high-speed serial interfaces. Simple and low cost, relatively speaking.
Okay, so Intel had AIB. Who else?
Then you have NVIDIA's NVLink C2C. That's a memory-coherent, very high-bandwidth interconnect. This proprietary tech allows them to effectively fuse a Grace CPU and a Hopper GPU into what they call a superchip.
A superchip.
It provides immense bandwidth, vastly superior to standard PCIe, and allows the GPU to directly access the CPU's high-performance LPDDR5X memory. That's a type of low-power, high-data rate memory,
Right.
which is crucial for massive AI and high-performance computing workloads.
So these proprietary links were powerful, but limited the mix-and-match potential.
Exactly. The industry quickly realized that proprietary interfaces wouldn't work for a broad ecosystem. That's why the dawn of standardization arrived. The Universal Chiplet Interconnect Express, or UCIe.
UCIe, that's the big one I've heard about.
It is. It emerged as a pivotal open standard. It provides a common language for seamless communication and integration among diverse chiplets, and its physical layer is actually based on Intel's AIB technology.
Oh, interesting. Built on proven tech.
Right. UCIe, with its optimized data transfer, delivers significantly better I/O performance and power efficiency than typical serial interfaces. Crucial for a truly integrated multi-vendor chiplet system.
And there's another standard often mentioned with UCIe.
Yes, working in concert with UCIe is the Compute Express Link, or CXL, another critical open standard.
CXL.
CXL is a cache-coherent interconnect built on the physical layer of PCIe, but it uses unique protocols to provide high-bandwidth, low-latency connections for accelerators and memory buffers.
Cache coherent, meaning they can share memory easily.
Exactly. Its ability to enable memory coherency and resource pooling is essential for heterogeneous systems. It allows components like CPUs and FPGAs to share memory space with low latency and without having to copy data around, which is incredibly efficient.
This move from proprietary to open standards like UCIe and CXL isn't just about convenience. It fundamentally democratizes hardware design.
It really does.
Imagine the innovation unleashed when smaller players can leverage best-in-class components from multiple vendors, accelerating specialized applications that were once too costly or complex. This isn't just a marketplace, it's a reshaping of who can innovate in silicon.
Well said. It opens up huge possibilities.
So where do FPGAs fit into this new modular world? I've heard them described as a flexible cornerstone. Can you elaborate on what that looks like in practice?
FPGAs, or field programmable gate arrays, have a unique DNA of flexibility that makes them incredibly valuable here.
DNA of flexibility, I like that.
Yeah. Unlike a CPU that runs fixed software instructions, an FPGA is a matrix of reconfigurable logic circuitry that can actually be rewired at a hardware level.
Hardware level rewiring.
Exactly. You program it using hardware description languages, essentially transforming it into a purpose-built chip for your exact task. This provides massive parallelism, extremely fast speeds, and eliminates operating system bottlenecks.
So, super adaptable.
Very. For years, FPGAs have been the go-to for hardware prototyping and emulation, especially for complex multi-billion gate designs before an expensive tape-out, that final design sign-off for manufacturing a custom ASIC.
Testing the big designs before committing.
Precisely. A great example is the AMD Versal VP1902. It's a chiplet-based adaptive system-on-chip specifically designed for emulating the largest modern chip designs. It essentially allows us to simulate future complex systems with chiplets.
That concept of FPGAs acting as flexible glue sounds incredibly powerful in this new modular world. How do they connect all these disparate parts?
Right, the flexible glue. The modular architecture of chiplets, while advantageous, can introduce interoperability challenges because you might have different protocols, different process nodes, potentially different vendors' components.
The Tower of Babel problem again.
Kinda, yeah.
Yeah.
This is precisely where FPGAs truly shine as flexible glue. An FPGA chiplet can be programmed to translate between these different interfaces, manage data flow, and provide the custom logic needed for seamless communication within a multi-die system.
So they act like universal translators and traffic cops.
That's a pretty good analogy. For instance, Intel's Agilex FPGAs leverage this concept. Their main FPGA core die connects via EMIB to dedicated I/O chiplets, or tiles, which provide advanced functionality like PCIe Gen 5 and CXL interfaces.
Oh, the tile.
Yeah. This means the FPGA gets high-speed I/O and memory coherency without having to implement those complex functions on its core logic die, allowing Intel to tailor different products for specific market needs.
Very clever modularity.
And beyond just connecting things, FPGAs also serve as task offloaders or accelerators in these heterogeneous systems.
Doing specific jobs really fast.
Exactly. They can handle specific high-speed parallel tasks that would otherwise bog down CPUs or GPUs. Think network function virtualization, database acceleration, or video transcoding. A dedicated FPGA chiplet can be tightly integrated to manage these parallel workloads, freeing up the CPU for more general-purpose tasks.
So far from becoming obsolete, chiplets actually make FPGAs more strategic and relevant than ever.
Absolutely.
It's a fantastic example of how a new paradigm can elevate existing powerful technology.
Couldn't agree more.
It's one thing to talk about the theory, but who's actually making this happen right now? Our sources show us how the big players in the semiconductor industry are already building their roadmaps around chiplets. This isn't just future tech, it's actively reshaping the present.
That's a crucial point. Let's look at some key players. AMD was an early and influential pioneer with its chiplet-first philosophy.
Yeah, Ryzen really shook things up.
It did. They proved the economic viability with their Ryzen CPUs, strategically placing high-performance cores on advanced nodes and less critical I/O on cheaper, more mature nodes.
That cost optimization we talked about.
Exactly. They used their proprietary Infinity Fabric interconnect for high-speed communication between their chiplets and are also committed to supporting open standards like UCI. Their versatile adaptive SoCs, as we mentioned, are also chiplet-based and critical for future chip development.
So AMD is all in. What about Intel?
Then there's Intel, with a long legacy of integration. They've shipped millions of chiplets in their FPGAs and pioneered the use of their EMIB packaging technology for connecting chiplets, starting with their Stratix 10 family.
Great, EMIB again.
Their Agilex FPGAs demonstrate this modularity by combining the core FPGA die with specialized tiles for capabilities like PCIe Gen 5 and CXL interfaces, allowing them to optimize products for different applications. And Intel's leadership in developing UCI based on their own AIB tech really shows their commitment to an open ecosystem.
They helped create the standard.
They did. And we can't forget NVIDIA's superchip paradigm. Their Grace Hopper, or GH200 superchip, for example, fuses a high-performance Grace CPU die with a powerful Hopper GPU die into a single package.
CPU and GPU living together.
Very closely. The key here is their proprietary NVLink C2C interconnect. It offers incredibly high bandwidth, significantly faster than standard PCIe, and provides memory coherency. This enables the GPU to directly access the Grace CPU's massive LPDDR5X memory for those huge AI and high-performance computing workloads that demand seamless data flow.
You can clearly see a shared direction here. Even with proprietary technology sometimes playing a role, every major player is moving towards this modular, integrated future.
Definitely.
It's truly becoming the industry standard for pushing performance and efficiency in advanced computing.
No question about it.
This all sounds incredibly promising, but no major shift is without its challenges. What are the big complexities the industry is still grappling with when it comes to chiplets?
You're right. There are significant complexities in what's known as co-design, integrating everything smoothly.
Co-design. Okay.
One major hurdle is power and thermal management. Integrating multiple high-powered chiplets creates a big energy problem with dynamic power profiles and complex heat dissipation paths.
The heat problem magnified.
Exactly. Different chiplets can have dissimilar physical heights and are built on different process nodes, which complicates the application of thermal interface materials and managing heat effectively. New cooling solutions, like two-phase immersion cooling, are becoming necessary to manage this increased power density.
Immersion cooling. Like dunking the whole thing.
Pretty much, yeah. It's getting serious. Then there's the monumental task of design and verification.
Making sure it all works together correctly.
And that's far more complex than monolithic designs. It requires new methodologies and tools to account for cross-die dependencies, how electrical noise propagates across different components, and the thermal impacts that can radiate from one chiplet to its neighbors.
Wow. Yeah, that sounds complicated.
It demands a holistic, system-level design platform that can aggregate data from chip, package, and board designers all at once. A really integrated view.
And what about interoperability? You mentioned UCIe, but is it perfect?
That's a big one. Interoperability. While standards like UCIe provide a crucial common physical layer, they don't guarantee that chiplets from different vendors will function together seamlessly at a higher logical level.
So, not quite plug-and-play Legos yet.
Not quite. There's still a significant hurdle to overcome for a truly open marketplace where any UCI chiplet is genuinely plug-and-play. A truly robust ecosystem will need standardized verification and resource management protocols to ensure full interoperability beyond just the physical connection.
So it's not just about the hardware. The entire design ecosystem needs to evolve, from software tools to design processes. But despite these hurdles, the growth projections for chiplets are astounding, suggesting the industry is full steam ahead.
Absolutely. Building this comprehensive ecosystem is crucial. We're seeing the development of new electronic design automation, or EDA platforms.
Software tools for designers?
Exactly. Specifically designed to streamline the chiplet design process and allow different chiplet designers to collaborate seamlessly. This collaborative effort is fueling what is projected to be a period of staggering market growth.
How staggering are we talking?
Well, the market for chiplets is estimated to grow from around $6.5 billion in 2023 to an incredible $148 billion by 2028.
Wow, $148 billion.
That's an exponential compound annual growth rate. This growth will be driven by the adoption of heterogeneous computing in critical fields such as AML, high-performance computing, cloud computing, and automotive technology, all areas demanding specialized performance and cost efficiency.
The demand is definitely there.
Oh, yes.
What an incredible deep dive into the world of chiplets. We've seen how the limits of traditional monolithic chip design have forced an ingenious shift to a modular approach, enabled by advanced packaging and open communication standards. It's a fundamental re-architecture of how computing is done.
And the unsung hero, the FPGA, really shines as that flexible glue for this new era.
Yeah, the flexible cornerstone.
Their inherent reconfigurability makes them essential for bridging disparate chiplets and accelerating complex workloads. This isn't just a clever idea, it's a foundational reimagining of how integrated circuits are designed and manufactured, setting the stage for continued, unprecedented innovation in computing.
This shift ensures that the relentless progress of computing can continue, even when traditional methods hit their wall. So the next time you hear about a new AI breakthrough or a super-fast new processor, ask yourself, is this made of one giant monolithic brain? Or is it a marvel of tiny, specialized Lego blocks working together perfectly? It really makes you think about how unseen innovation impacts everything we do, right down to the silicon.
It really does. A fascinating transformation happening right under our noses.